Topic will be photomodulation, PBM. The benefits of low-level therapy and laser devices for healing, rejuvenating, regenerating, and protecting tissues. Such an excellent topic. If people are not here, they are missing, we are helpless. The speaker will be today Dr. Francisco Jose Cidral. Yeah, no. I'll call him. Has led 18 research works with 170 citizens and 150. Please come on the stage, sir. Please sit there. Role of introduction 10 and antioxidant enzymes. He is a co-founder and associate professor of the laboratory and experimental neuroscience at the UNISUL University in Brazil. He is a published researcher in the area of integrative medicine, low-level light therapy, and neurobiology of pain and inflammation. He serves as associate editor of the Journal of Naturology and Complementary Therapies, the Rheumatology Open Journal, the Journal of Yoga and Physical Therapy, and the Journal of Orthopedics and Sports Medicine. He holds a bachelor's in Naturology, Integrative Medicine, specialization in traditional Chinese medicine, a master's and a PhD in neuroscience, and a postdoctoral fellowship in health sciences. He is the Director of Research and Development of Multiple Energy Technology LLC and founder CEO of Scientific Consulting LLC and Natural Quanta LLC. Sir, I request you to start up.
You just have to tell me if I'm speaking clear enough. Sometimes I speak very low, depending on the, yeah. Okay. Is it better now? Okay. Well, first of all, thank you very much for inviting us here. Thank you all for the hospitality. I have to say that your customs are very different from the ones that we have been exposed to in Brazil, especially in the US. You make us feel very, very, very comfortable, and I find that I have a very big affinity for your ways, being a vegetarian myself, and a person that believes that this is not our only life, that we're here for many other times, and we have met in different occasions, and I think that everything that we are talking about here, as Patrick said, is something that we have already discussed in the past, and now it's the time, apparently, for the world to remember the non-invasive integrative approaches to health that we have forgotten, because there was a time in our development that we had to go through, if you can't see, if you can't touch, it doesn't exist. But now we have technologies to show that even light, energy, electricity, and everything else, maybe like 100 whatever years ago when we started talking about it, it was like magic. But now we can actually measure it. You can measure the effects, we can see what it does to the body, and we can very clearly explain the effects of photobiomodulation. When you shed light in your body through different pathways, you can see what happens inside of the cell, you can see what happens inside of the organelles, you can see the proteins that are expressed because of that, and not just any type of light. You have to be specific. It's like the drugs. If you give half a dose, you're not going to have the effect. If you have a wrong dose, you're not going to have the effect. So there is a very concise and very well-researched database now in the literature to explain the effects of light and photobiomodulation. And I'm very glad that I was, in a way, a part of that development, because when we started back in the day, we didn't even call it photobiomodulation. People called it chromotherapy or light therapy, and then the name started to appear. We started to do the research. When I got first interested, I was still a student at school. My course is a little bit similar to what naturopathy here in the US is. It's just a different name. It's a 4.5-year full-time graduation program. And then you pick a specialty, and then you go through another 2.5 years full-time. And so I did my specialty in acupuncture, Oriental medicine. But I always, ever since I was a student and we were exposed to light therapy, I always thought this is my calling. This is something that spoke to me, because it's non-invasive, it's light. I mean, being an acupuncturist and having more than what I think back in the day was 200 or almost 300 hours of clinical acupuncture, I do it, but I always prefer to use lasers or LEDs, because I see the same effect or the same results. I can actually modulate it better. And also, a lot of people, they're afraid of needles or don't like needles. And also, I mean, there's no chance of risking of any infections or anything like that because you're not breaking the skin. You know, so it made a lot of sense to me. And then I decided, well, you know, after seeing all the results, but how does it actually work? We see the results in the clinic. I started to teach after my graduation, after my specialization and everything at the university. They called me in because I was like a low-level light therapy fanatic back in the day. When I was a student, I helped write the book that now is used at the university because I really got into it. And then when I was, you know, doing my years, I was always working at the clinic together with the professors and developing new ideas and new things. I have a very good knack for languages, so I could read in different, you know, languages what was being published in English, in Portuguese, Spanish, Italian, German, French, you know, and I know a little Chinese too. No Hindi or no nothing for now, but maybe next time, just watch me. Anyways, so I was always collaborating, and then I decided, but I have to understand this a little bit more, so I went into neuroscience, and I got into a lab that was, I was, you know, very happy that the professor, who was a pharmacologist, you know, very square, you have to block the receptors, you have to do this, and I said, I'll be very glad to do it, because I really want to see what it does. And then we started doing it, you know, following a pharmacological approach and looking at all the different receptors, first with general models of pain and inflammation, and then we started looking at neuropathic pain, you know, different pathways, brain activation through low-level light therapy, and so on and so forth, so that I could understand what he was doing. And I think that because of our work and the things that we do, we never do it alone. We do with people from the university and the lab and professors and other students that are working together with us. We did some very nice work, got some important papers published in Journal of Neuroscience, Pain Journal, European Journal of Pain, so A1 scientific journals with very high impact factors. And then because of that, actually Porter heard about us and our work and research, and then by the time I was already living in the US, so he invited me. We had a conversation, and it was like an instant, well, I like this guy. I feel good. We speak the same language, and now I'm working together with him to help develop the new products and everything else. So I would like to show you the university where I studied. This is just a picture of the city first, so that you have an idea. A map of Brazil, and this is where Florianópolis is located. It's quite far from here. Yeah. It's actually an island. It has about 42 beaches with sand dunes, and it's a very beautiful place called Florianópolis. We have a very famous bridge down there that a lot of people talk about. It's like a landmark. And because we were visited by the Portuguese back in the 1600s at the very beginning, I mean, we all speak Portuguese. It's very different from the Portuguese that is spoken in Portugal. Like the English that you speak here is different from the one that we speak in the US or in Great Britain. And so this is some of the dunes and some picturesque places. I'm showing you this because the idea is for us maybe to have a conference there, and then you guys can come to Brazil. You know? Yeah. For me, the main idea, I mean, we could go on about low-level light therapy for 3, 4, 5 days with all the different protocols and all the different studies. There's more than 600 studies on low-level light therapy alone, explaining the mechanisms. And there are a lot of different protocols. And I'm just talking about photobiomodulation as something very scientific that you can look at and you measure the effects in the physical body. But we know that we're not just a physical body. There's a lot more to us than that. I mean, that was the last part of it, I guess, that makes it useful for this planet over here, but we're a lot more than that. So we're not even talking about the other effects of low-level light therapy, photobiomodulation, and with the chakra alignments and all that, you know, in the energy body with the information that the light can provide. I'm just going to try and be more, maybe tomorrow we could talk a little about the other aspects, but today I'm going to talk about some very physical, some very scientific. If you allow me, that makes sense. This is Dr. Daniel. He's a physical therapist, also a neuroscientist. About, I think, 10 years ago, more or less, we started the lab of experimental neuroscience at the university. This is the University of Unisul, the one that I told you about in Florianopolis. This is one of the locations. The university has, I think, 6 or 7 different locations like this, about 25,000 students, more or less. Yeah, including all the different locations. And we have courses in integrative medicine. We have actually an integrative medicine clinic only for that. And we also have then a clinic, a hospital, physical therapy, sports medicine, nursing. There's all that, apart from, the other that are not part of the life sciences. And the lab has about, for now, I'm still supervising some students that go through their master's and the PhD in neuroscience and health sciences, and they travel there sometimes to teach some lectures and do some work at a distance. But Dr. Daniel stayed at the university, and now it has about 10, 12 different professors. Each professor has maybe 6, 7 PhD or postdoctorate or master's degree students, so it produces quite a lot of work. The lab has had so far about 300 and something publications alone, and it's specialized again in integrative medicine. So we do a lot with photobiomodulation, but we also have a lot of papers on acupuncture. We have a lot of papers on natural substances. That Brazil is very big in biodiversity and very big in different natural extracts. So there is a whole line of pharmacology dedicated to that. And also physical therapy approaches like ankle joint manipulations and soft touch techniques as well. And these are some of the students of the lab. And I also would like to mention the relationship that we have with education through the Salgado Institute of Integrative Health. He's a doctor of physical therapy, a nutritionist, a doctor of osteopathic medicine, and has a master's and a PhD in biomedical engineering. And he was also studying the effects of low-level light therapy together with me. His institute has been in the country for like 25 years, does a lot of research. We've had about 40,000 students so far. And there is a chapter in Portugal for 15 years, and now we're bringing this institute to the United States through what we call the Integrative Health School. And we're just starting this. We actually, this logo, this is the first time I show it. And we just got the website, and then we're going to start developing a lot of courses in integrative approaches to health. And this is in the United States because I now reside in the US for about 7 years now. I came because I was studying another part of the spectrum. It's still photobiomodulation, but I'll show you. So we're going to talk a little bit about this, near infrared and a little bit of red, which is the part of the visible spectrum. But this part over here is far infrared. I don't know if you have heard of it as well, but I know Rita has talked about it. This has a lot of therapeutic effects as well. It's somewhat different, the mechanisms of what it is doing. Maybe we have some time on some other day to talk about it a little bit, but this is what brought me to the US. I was studying the effects of infrared, mostly near infrared and in the visible spectrum, and then I decided to start investigating far infrared, but I was doing that through not devices, but I was using our body heat, because we produce far infrared the whole time. That's why they use special goggles, and people can see you even if there is no lights, because you are emitting far infrared the whole time. That's the technology that is used by the armies everywhere. It picks up your heat. We're actually batteries, so we're producing this the whole time through various mechanisms. And think of this, if we're producing it, if there is a way of us to collect this information, modulate it, and send it back to the body, maybe we have therapeutic effects, right? So what we did is we developed a specific, this is a fabric, like a shirt, that has a specific blend of minerals in there, and these minerals, because of their specific composition or chemical composition, they are very receptive to far infrared in the range of 8 to 12 micrometers, which is it's a lot of nanometers, it's like 10,000 or more. So they are very receptive to that particular signature or heat signature that our body naturally emits all the time. So it excites those molecules, and then when they decay, because nothing in nature is going to be forever excited, it decays back. When it does, it sends back the quantum energy back to you, this energy packages, in the form of far infrared at a specific wavelength, depending on the composition that you choose, and that has therapeutic effects. It has anti-inflammatory effects, antioxidative effects, and you can actually draw blood and measure in the blood the markers of inflammation, the markers of oxidative stress. So I developed this, and I brought this, we patented, and we found an investor in the US, and we developed a full line of applications with different companies. And these are, so that you have an idea, these are just some of the research that we published with this specific technique. So we could have like 2 days just talking about that research alone. I guess he has a question, yeah. Yeah, it reflects back infrared. You produce infrared. Oh, it's called, bioceramics or ceramics. Oh, there are more than hundreds of different types. This is research that has been doing, there are people, different universities researching this for the past, I think maybe 70, 80 years. What I did was I selected, because I had the devices and the equipment to measure, so I was able to be very specific. Some of these materials, they absorb maybe 40% of your energy. The ones that we developed absorbed like 80 something, 90%. Yeah, I could. Oh, good. Yeah, let's have some conversation about that. But anyway, so this is just the story of how I came to the U.S. to work as a chief science officer of the company that developed this, and then from there, I mean, we stayed. But the topic today is not far infrared, is near infrared, or the red part of the visible spectrum. And so before we even start, I'm sure that you all know what wavelength is, but we're going to talk about it and the importance of it. It's just a physical property of how the electromagnetic spectrum propagates in the vacuum or anywhere else. You're just measuring the distancing between the two different waves, and then 670 nanometers, that's the unit, and 950 nanometers, this is red, and this is infrared. It's over here. You can see around 700 nanometers or nanometers, up to 630, 670 is red, and then as you start to go down, like 500 around is red, and then you have the blue. This is very important because we're going to talk about because of this specific property of the wavelength, there is a penetration depth, and that varies with the wavelength. So we have to be very specific and select the correct ones. And then sometimes people say, well, low-level light therapy doesn't do anything, or light doesn't do anything, and yes, are you using the correct dose? Are you using the correct wavelength? Are you using the correct irradiance of the device? Are you exposing the patient to the appropriate amount of time so that they get the specific dose that they need? What is your treatment regimen? Do you do this like once a month? Then, what drug does that? So it's very specific. It's no, hocus pocus or anything. You can really measure it. But before we even start, I just have one thing for you to think about. So nobody has any questions that microwaves can have a very interesting effect on your body. If you put your hand inside of a microwave oven, nobody's, because you see that every day in the kitchen, I wouldn't recommend it, but also everybody talks about the effects of X-rays. This is used every day. People see it in the hospitals and everywhere. And, gamma rays that causes cell damage. This is very, very, very well studied and very well known. There is a joke even with the Hulk. Right? Remember, he was exposed to gamma rays. See what can happen to people if you are. But anyways, and then I'm just talking about another range of the electromagnetic spectrum. If this does so much, this, and that, how come this part doesn't do anything? Do you really believe that? It's obvious that it does something. And this is what we're going to talk about. I mean, there's no way to contest that kind of information. Yeah, these are some of the things we're going to talk about. I'm not going to be able to go over everything today, but luckily we have tomorrow. you know. If I don't bore you to death today, then we can continue talking about it a little bit more tomorrow. And so I'd like to start with a little bit of the history, which I think is very interesting and apropos, because the first records on the use of light therapy as a whole, not just infrared and near infrared, I'm talking about the full visible spectrum, started here in India. So, I mean, we're here. Might as well mention it. So about the use appears in the Vedas in 1400 years BC, but actually the use has been like for more than 3,000 years. So it started here. Now I think that yes, it's coming back in a way. Yeah. And then only in the 18th century we started to have some more records of the use of light. I mean, look how many years it went by before people started to realize that this was so important. You know. And in the 19th century, this started to become important. Heliotherapy, which is the use of the sunlight directly for therapeutic purposes. It was very big in Germany. It's very big in Italy with balneotherapy, or the effects of water and hydrotherapy. Those countries in Europe are very big on this. But you can be a lot more specific because, as I showed you, it's a big spectrum. And each one of those little parts has a specific purpose. Each one has a specific purpose. For instance, when you talk about the blue light, you're going to see that later on, then the effects are more on the skin because it doesn't penetrate. So you have one thing that every baby in the hospitals are treated with when they have jaundice is blue light. You know? But anyways. So, and then I just thought there was a lot more to the story, but I just thought I would say that the Nobel Prize for Physiology in 1903 was by a Danish doctor, Dr. Niels Finsen. There is a huge institute there, so he won the Nobel Prize for that, for low-level light therapy. And then after that, it looks like it went down the drain, and people started, this is, well, it's coming back now. So that was for the use of light as a whole, but there is a special chapter, which is red and near infrared that we talked about. That is the story of photobiomodulation. Started with low-level laser therapy because the device was a laser, and this was the doctor that started this by chance. They were talking about the effects of laser as cellular ablation to remove cancer or to cause even cancer. Depending on the amount. So we're talking about a very high dose, which is not low-level light. It's high-level light or high-intensity lasers, which are used every day in surgeries, right? So he was conducting an experiment and doing incisions and implanting tumor cells and then treating with cancers to see the proliferation, or also he was also trying to see if he could decrease the cancer cells with the high-intensity low-level light therapy, but then he was not having those effects, and then by chance he noticed that actually the hair started to grow faster and the healing was faster. And then he had his laser investigated, and he was supposed to be, I think, like 500 watts per square centimeter or something. It was actually like 5 or 10. So he said, wow, this is another dose. So if you change the dose, you have completely different effects. You're not destroying the cell anymore, which is very good for kinds of specific kinds of applications, but you're seeing other effects. The ones that are stimulated it somehow, but how? So he was the one to start talking about photobiomodulation by chance, and that's how it started. And then he published a lot of research on that. He did a lot of studies, and so but he was the first one to talk about this B phase response, 2 different phases: high intensity, low intensity. And this was lasers, laser diodes. And there are differences between the lasers and the LEDs, but back in 1988, we didn't have the technology for light-emitting diodes to be specific enough on the way that it produced light. It was scattered all over the spectrum. The LEDs would, and then actually scientists by NASA in the US developed a specific type of LED that has been called ever since NASA LEDs, that were much more precise and had a lot more irradiance, because the dose from the LEDs were like the ones that we have on TVs or in the computers were very low, didn't do anything, didn't penetrate, and it was all over the place. Now they were able to do something very specific, and the way in terms of wavelength, there's still a little variation from 10 to about plus minus 10 nanometers, but that's good enough because the peak of emission is very precise, and also the radius is much higher. That opened the door to something that is called LED therapy, which is, I'm going to talk a little bit about more, but there are a lot of benefits to it. We studied both in the lab. We have publications with laser acupuncture, with just laser biostimulation, with LED acupuncture, LED photobiomodulation, transcranial photobiomodulation, with lasers and LEDs, with the combinations, with just one, just the other. I mean, there's a lot there. And these are the so-called NASA LEDs, and you can see here they use it quite a lot for plant growth because it stimulates metabolism. So, I mean, look, if it is something that NASA uses on their ships and they're doing research with, and they have seen their results, I mean, they don't spend money on things that don't work, It works. I can tell you that. And if it works in your body, why not on the plants? In plants and animals, Of course it does, same principles. And also they have a lot of problems with wound healing in space, and because of gravity and all that, so they use it a lot for wound healing as well. Ever since this, I mean, LED therapy is much more used, and we have now super LEDs that produce a lot more energy than those. Those are back in the 80s. I mean, there has been a lot of advances for now. Just to call your attention to some of the things, I already talked about it, but here we have the first one, lasers, right? Light amplification by stimulated emission of radiation. And then there is a lot of different names that people call it. You say low-level laser therapy, low intensity or high intensity laser therapy, low energy laser radiation, and then the LEDs that we talked about, light emitting diodes. And there's a lot of publications that go by the term light emitting diode therapy. We actually have a couple of them where we call it that way. But now the correct term for triple LT, which is LLLT, it started in the literature with low-level laser therapy, is now low-level light therapy. That's the way to call it now, because this is incorporating also the use of LEDs, or light emitting diodes. And this is a term that appeared not so long ago, but makes a lot of sense, photobiomodulation, or photobiostimulation, because of you're shedding photons or light energy inside of your body through different ways, and you're getting biomodulation. You're modulating body responses. It's not like giving a drug. You give a drug, and then that drug generally is going to connect to a specific receptor in your cell. You have thousands of them in each of the cells, depending on the cells, and then stimulate something. Maybe there is going to open a channel. Maybe it's going to stimulate an internal pathway, and generally it's going to somehow affect, most likely, a pathway that involves NF-kappa beta, and then it's going to have some activation inside of the nucleus of the cell, and then an activation of or an expression of specific proteins, and then you have the results. But the drugs, as you know, they do a lot of bad things as well. So one of the things that struck me was very interesting when we first moved to the U.S. is that in the United States, you cannot have a commercial or TV commercial for a drug if you also do not talk about the bad part of it, or the contraindications, or the accidental responses. And then generally the commercials last like 3 minutes. The first 30 seconds they say, this new drug is good for this. And then in the rest of the 2.5 minutes, they go, but this is bad for that, and this bad could lead to this, it can cause death. Wow. This actually doesn't. Why? Because it's not exogenous. It's to stimulate endogenous receptors and endogenous substances. If we have a opioid receptor in your body, it's because your body's producing something for that. Otherwise, it wouldn't be there. Nature doesn't, waste energy or time. So there has to be a way that you can activate something, endorphins, that are going to connect to those opioid receptors and reduce your pain. That's what it does. It already activates a mechanism that is there. That's why no contraindications. We don't recommend for pregnant women and all that for the obvious reasons, especially in the U.S., because the lawyers would be just waiting to sue you. But, Anyways, so in a brief description, photobiomodulation, I can read that with you. Non-ionizing electromagnetic energy, and we already talked about the electromagnetic spectrum, and so low-level photonic emissions, typically within a specific wavelength range, and we talked about the wavelength range as well, because if you're out of that, you don't have the effects, or you have to be way over it to be far infrared. So non-ionizing electromagnetic energy, typically within a specific wavelength to trigger photochemical changes within cellular structures that are receptive to photons. So there are certain structures in your body that are called photon acceptors. Here are the examples of our photosensitive structures. Here are some of the examples. Green light, blue light, near infrared and infrared. Everybody heard about the effects on the mitochondria. That's mostly with the red light and the near infrared spectrum. Why the mitochondria? Well, first off, it's very important because it generates energy. It's our energy generator inside of the body through a chemical reaction, storage of transformation from ADP to ATP, and then when you spend it, you give the energy back. So it is done through an electron chain inside of the mitochondria membrane, and there are different complexes that are part of this process. Complex number 4, which is called cytochrome C oxidase, happens to be a photon acceptor. When you shed light at the right wavelength and at the correct amount on the mitochondria, then you have an instantaneous reaction. There is a little bit, I'll show that later on. There is a little bit, well, maybe later on. It's on the next one. But I'll show you that. But anyway, so this is just to demonstrate that mitochondria is one of the photoacceptors. I have to change the order of this. So photobiomodulation, why? Low risk, very low risk. We already talked about it. Inexpensive, especially if you're using LEDs. An LED is way less expensive than a laser diode. Very cheap. LEDs, sometimes you buy them for cents. Of course, the proper technology to use it and everything else, they end up being a little bit more expensive devices, but a laser device could cost in the US like $10,000 or more, $16,000 depending on what it is. And if you do a combination, like I'm going to show you one maybe tomorrow or the day after, it's like 4 or 5 times less. So it makes it more accessible and very, very practical. And so modulate cellular functions, proliferation, migration, tissue regeneration, wound healing. I'm going to show you a little bit of some of the results that we get with that. Here are some additional, I don't have time to go over all the research for each one of these effects, but this is so that you have an idea. This was a review that was published in 2011 showing all the different mechanisms that are already validated and proven through double-blind, randomized scientific research of the effects of low-level light therapy. So biochemical effects on the mitochondria, fibroblast proliferation, mast cell degranulation, macrophage activity, keratinocyte activity. We actually were the ones that published this. Increase in oxidative stress, also bioelectric mechanisms, electromotive action on the membrane-bound ions. So you can actually open or close specific ion gates, and then ions enter the cell, and then you have specific activities, intracellular, extracellular, and so on and so forth. So this was the one that I was supposed to show you before. This is the mitochondria, and then you're shedding light on it. And then this is the cytochrome C oxidase inside of the membrane of the mitochondria. So it's exposed to light. As you can see here, there is a little bit increase of reactive oxygen species, or because of that, a little bit of oxidative stress. But remember, even in homeopathy or in other integrative approaches, you give a little bit, then your body reacts. So you stimulate a little bit, just enough, so that you have an activation of the antioxidative pathways inside of your cell, which are the production of superoxide dismutase, catalase, and I'll show you the results of the test that we did it and how we did it, and then you draw blood from the patients and you see the result there in the blood. So there's incontestable evidence that it works. So it activates, there's a little bit of burst of oxidative stress, and then an activation of ATP production. This activates the antioxidative effect inside of your body and stimulates the production of antioxidative enzymes. And then you have an antioxidative effect. You have anti-inflammatory effects because there is an activation of internal cellular pathways, including NF-kappa beta. And we know that because we blocked those and then we didn't have the results. And then we let it go and then we saw the results again. We can pharmacologically block each one of those steps. And then, well, it doesn't happen now. And then you know, oh, this is involved. You can be very specific nowadays, and look at each one of those components in the pathway, and then you can measure the outcome in the blood. So this is incontestable truth. And then you can also see, because of this activation of intracellular pathways and expression of specific proteins, that we also have anti-inflammatory results with reduction of inflammatory cytokines like TNF-alpha, and also depending on the specifics of the wavelength and the dose, we can also have an increase in anti-inflammatory cytokines, for instance, interleukin-10. And I'll show you the results of that. But anyways, and if it is in the brain, it actually activates more pathways, and you can see that. And then we did that test in the lab with functional MRI at the same time. And then you're doing the low-level light therapy, and you see the increase in the activity in specific areas according to the areas that we treat. So this is very, very specific. And increase in these, and you can measure these, neurotrophic factors in your brain, which help your brain growth and regeneration and all that. I think we're going to have the questions later on. Yeah, so neurogenesis, remember that Porter was talking about it? Neuroplasticity and neurogenesis, stimulated by transcranial low-level light therapy. So these are the mechanisms. I'm not going to be able to show you the research for each one of those, but I'll show you some, and some more also that I thought that was very interesting. Probably tomorrow, because we're not going to have time today. So I don't know how I'm doing on time. I have 10 minutes or 10 more minutes, okay. So yeah, we have more time tomorrow and the day after, but anyways. So let me talk a little bit just about the parameters. And this is something very, very, very important. It makes a difference between the effect or no effect, and we have to be very specific with everything that we do. And the parameters are very important. Why am I insisting on this? Because this was something hard for us to understand at first. We would say, let's test the effects of low-level light therapy. What do we do? What is the wavelength? What is the dose that we give? And then we're given the dose, and then, but I have 2.5 joules of energy as a whole per square centimeter, but it's not doing anything. And then it was the irradiance of the device. And then when you look at literature, people are comparing apples to oranges. There is a research that is showing, the laser is way better than LED. And then you look at the wavelength is different. The irradiance is different, and the dose is different. Of course it's different. Right? So we actually developed something to study that. But anyway, so as a basis, I already talked about this. If you have too much of the low-level light therapy, the dose is too high, then you can damage the cell, increase temperature. As the photodensity increases, you have energy. Look, 40 degrees Celsius, 50, 60, 80, 100, you can burn. Depending on the intensity. That's the amount of photons that are emitting by every second. And so you have high-level laser therapy or high-level light therapy. You could do that with LED as well. But we're talking not about this part, we're talking about this part, which is depending on the photon density that you have to choose, of course, you don't have any heating of the tissue. You don't actually feel it if you're using the correct dose. Not that the heating is bad, but sometimes may be uncomfortable, and you don't need that. There are specific receptors, even with the far infrared that we talked about, that is basically getting your body heat, and returning it back, because the level of the irradiation is so low, but you're wearing this overnight. For instance, we published a study with Dr. Von McCall from Medical College of Augusta, Georgia, and he is, I think, number 3 or 4 in the world for sleep. And that was the first time he investigated something that was not a drug, which was the bed sheets with the ceramics. And he said, I've never seen anything like that is not a drug. but you're sleeping with it. So over the whole night, you have the effects. It's a small dose over a long period of time. In that case, it works that way. And it does not, and here either, it doesn't either, it does not activate the receptors in our skin. They are called the vanilloid receptors, TRPV receptors. They're not activated, so you actually don't feel any heat. You know, it's just, anyway, but you have to control that. So the dose is very important. Here I'm talking about one aspect of the dose, which is the radiation from the actual device that you're using. When I do this, how many photons do I have in this red dot? You know? So, and it could have a lot more or a lot less. So that's one of the things that you have to regulate. And not only that, the dose, and this is the interesting aspect of it. The dose also has to do, of course, with the response that you get. If you have a dose that is too low in terms of joules per square centimeter in your body in the emission, you have nothing. You know, very, very small dose. There is very little cellular change. Remember, you have to do something to the cells. There has to be an activation, a substance that is activated, that receives these photons and then does something. Otherwise, nothing is happening physically. Again, we don't know about the other aspects. And then you start increasing the dose, you start increasing the reaction. And then it gets to a point, it plateaus, and then it just continues like this. You continue to increase the dose, but the response is still the same. And then if you go overboard, then you start to have the opposite effects. And this is very, very typical response and very curious one. A lot of drugs act this way as well. Because if you have those receptors there on the outside of the cell and you have the ligands or the particles or substances or whatever that connect to those specific receptors, after some time, if you continue doing it too much, then sometimes, as in the case of peripheral mu opioid receptors, as a response to continuous morphine doses, you have the interiorization of the receptors, and that doesn't work anymore. So you overload the cell, and then you don't have the effect. So the dose has to be very well calculated for that, counting for refraction, absorption, and all those kinds of things. Different color skins, they have different substances in there that may attract or not, you know what I'm saying? So all that has to be looked at. This is actually one of the studies that we published back in the day, when we're looking at the dose, and we're calculating the response here, the pain response to the different doses. If you see there, you see 1 joule is not doing anything, it's not reducing pain, as a response to a noxious stimulus is 100% of the time. And then as you increase the dose, then you see a better response. And then if you continue to increase this, then the response starts to reduce. So exactly like what we see here, but this is of course inversed. And this was published, I don't remember when, but some time ago. So that's one thing. And then we also talked about wavelength. Remember that? So the wavelength, this is a very simple example. Look, this is green light. You're shedding it through your finger. It does not cross to the other side. If it were blue, you wouldn't even see this. You would just stay in the surface. Now, when you do it infrared, look, it completely crosses to the other side. And I'm talking here about the same dose. It's just the penetration depending on the specifics of the wavelength. And then you see here, as you increase the wavelength, it starts to penetrate. And then around 1,000 nanometers, the molecule that is activated is water, which we have a lot. And then we don't have the effects anymore. So until you get to maybe 40,000, and then that's far infrared, then you start to activate those same water molecules in a different way. But this is the topic for another conversation. So here is a very visual, graphical explanation for that. Depending on the specifics of the wavelength, then you have the different penetrations, and it could go to the hypodermis. Really, depending on the, of course, again, depends on the irradiance that you're using and everything else that you're using on the different parameters. And here are some of the molecules that are activated according to the specific wavelength. So this is the therapeutic window, that's why I call it, in level light therapy, for that kind of, photobiomodulation, activation of cellular and also blood organelles and whatnot. So it has to be absorbed. There has to be a molecule that is physically changes, or activates a pathway or something. Intensity of the stimulus, very important, so you have to really know how to calculate this. Generally, we talk about milliwatts per square centimeter when you're talking about radiation, so it's a specific dose. And here, when you use this through the area, then you calculate what is called the energy density or fluent, which is the actual dose that you're giving the patient in number of photons, and the wavelength has a specific therapeutic window. So it varies in the studies from irradiance from 5 to 100 milliwatts, the dose from 1 to 100 joules per square centimeter, depending on the application, the area, sometimes it's spread out, through a specific area, the wavelength, and there's a lot of applications for blue, for near infrared, for red, for whatnot. Treatment interval varies in the literature from few hours to days, and the number of treatments too. We have developed over the years many different protocols for many different things, and then we go to the lab, and then we take it to the integrative medicine lab, and then we get the students involved, and then we see the results, and then, and so on and so forth. And talking about just, over the skin, with transdermal applications, there are so many other different ways of doing it, right? Just to show you the importance of all these parameters, and that's why I wanted to hammer it out, think about the parameter. When you go buy a device, look at the parameters. Look if you can control them, if they are inside of this window, otherwise it's not going to work. These are just different wavelengths and combinations, different number of treatments, irradiance, fluences, and everything else, and I'm just talking about dermatology. So there's a lot there to talk about. We could have like a week of low-level light therapy conversation with the protocols and everything else. I'm just going to show one last thing, and then we can go to the next talk, and then we continue tomorrow. But remember that I talked to you about their comparing apples to oranges out there, because there is no device to do it. So we went to the engineering department at the university, and we said, we want something that we can have 3 different wavelengths at least, but we can control the irradiance and we can control the dose. So we can just select one of those things and then test side by side, just varying one thing. So we developed this, and then we control it through the computer, and then we have a specific output so that we can do the research. And I'm going to show you just one of the examples. There is a lot more. This is an example of the same wavelength, which is red in this case, not in the infrared spectrum, of 630 nanometers. The dose, which is the amount of photons that is irradiated, generates the energy equivalent to 2 joules of energy per square centimeter. This is on the skin, so transdermal application. And we just changed the irradiance of the device. The device is emitting more photons or less photons at that amount of time. And then look at the result. This shows an analgesic effect in the model of inflammation. So this is an anti-inflammatory response that reduces pain response. So reduce inflammation, reduce pain. Well, of course, they are all associated. And look at the effect when you have 90 milliwatts per square centimeter. Way more effective and more long-lasting as well, because this is the time course of one small application. So I guess tomorrow we can start talking about the differences between these two over here, and then I'm going to show you some of the research, how we reach those conclusions, and then maybe the other day we could talk about some of the protocols, and I'll show you like a couple of devices that I brought for transdermal and also transcranial low-level light therapy. I guess that's it. Well, thank you.